We're going to start off this video just finishing up the last little bit we had on the previous problem in which we had established a rate law. And now we're going to figure out what the rate constant is. So we'll actually write that down. Determine the rate constant, that lowercase k value. So what we can do is look at the previous problem. And again, I'll just kind of pull it up here. Where did I have that? In your notes. So looking at the previous problem, we can choose any line and use that as reference. Again, it's a rate constant, it doesn't change. So we can actually choose any of these lines and plug in the numbers that are present for the concentrations and the rate. I am just going to choose line 1 for no good reason. So I'm going to take these three values and plug it into our equation right over here for A and B, with understanding that these are the rate orders, second order and first order, and I know what the rate is, so I'm going to use these as the rate. Then again, I'm going to use line 1 and plug these values into it. Here we go. I will say 2.0 times 10 to the negative fifth molarity per second, that's the rate, is equal to K, 0.1 raised to the second power, and 0.1 raised to the first power. And if I do that, the answer is equal to 2.0 times 10 to the negative 2. And then look how the units kind of play out here. This is the K value to the 2 minus, and I am guilty again of switching the negative back and forth as I did here. That's just a bad habit of mine, so if you have a certain way that you like to do it, just stick with it. But I find myself doing that all the time. Not really an issue. But as far as the units, make sure you keep track of that. The way I kind of think about it is I know that the units have to finish up and be this for rate. I know it has to be this. This I don't know. But if these are concentrations, which means it's a molarity, I know that this is m to the second and this is m to the first. Together they make m to the third. What does this have to be in order to knock this down to 1, but also to bring this s to the negative 1 value in? K must have units that are m2 minus and s negative 1. So this is kind of how I can quickly double check and make sure that my units make sense for that. Okay, let's do a problem in your homework. And it looks like we're on 27. Excuse me, 37. If we take a look at this one, consider the gas phase reaction between nitric oxide and bromine. Here it is, there's the reaction. And we have the following data. This is very, very similar to the problem we just did. So I have concentrations for these guys, and I have rates for all of them. What we want to take a look at here is basically what are we holding steady and what are we changing. So for example, if I want to know what's going on with bromine, it looks like I'm holding this constant nitric oxide in lines 1 and 3. And then here I'm going up by 2.5. Again, there appears to be no good reason why they're changing it in such a way. What's happening to the rate? So I know that the rate law is going to be written like this. What I don't know are the exponential values. So that's all I'm setting up for is given these two reactants, what are the exponential values or the rate orders for those two things? So on scrap paper, what I would do is I would take, for example, line 3 and divide it by line 1. I'm holding this steady, so that's not going to change. But if I divide 0.5 by 0.2, you're going to get 2.5. I'm going to write like this. 2.5 raised to some x value is equal to taking 60 and dividing it by 24. That gives me 6.25. Now, if I take the log of both sides, because I don't know, now what I could do is just start plugging in values. Is it 0? Is it 1? Is it 2? And I could do this all day. Or I could set up an algebraic equation for this, take the log of both sides, and solve it this way as straight ahead and not have to go through that guess and check method. And I will see that x is actually equal to 2. Problem solved for that. If I do this for the other, wanting to know what's going on with bromine, I'm looking at, going on with nitric oxide. I need this to hold steady, so this is constant. And now for nitric oxide, same deal. I'm going to have 2.5 divided by x. And it is going to be equal to, taking 150 divided by 24, it's going to go up by 2.5. And therefore x is going to be equal to 1. So the coefficient values for that are going to be 2 and 1. Problem solved. Now for part B, calculate the average of the rate constant for the appearance of this NOBR for the 4 data sets. So what it's asking you to do here is, now that you know what the rate law is, plug in all the 4 lines and figure out what the average of that is. And if you do that, I'm not going to do it every single time, but if we do this every single time and plug in, okay, these values for nitric oxide and bromine, and figure out putting the initial rate in there for the rate constant, or for the rate law, the rate, and then figure out what K is every single time, you'll end up with 12,000. As far as what the units are for this, so we're going to use the same method we did before. I'm going to say, okay, well, if I have to have these units for the rate, and this is to the second, and this is to the first, that means that's to the third power. What does this have to be to make this true? And it's going to be exactly as it was for the previous problem. K is going to be equal to m to the 2 minus s negative 1. So that'll give us the same units we had on the previous problem. There we go. Problem solved. Back to the notes. All right, let's keep moving along, and we're going to change this a little bit. We're still dealing with the whole concentration thing, but we're looking at a change of concentration with time. We'll write that down. Change of concentration with time. And we're going to focus initially with a first order type reaction. And more specifically, it is a single reactant raised to the first power. And to kind of write this out to see what we're looking at here, we'll say rate is equal to the loss of that reactant A with a given amount of time. And what the rate law would look like for that is K A raised to the first power. Now this is going to sound a lot more complicated than it actually is or needs to be. So don't worry about what this is going to sound like. Using integration, a little behind the scenes calculus, what this would become is natural log of A at some time minus natural log of A initially is equal to negative rate law in some time. Or based on the subtraction we have here, we can write this a little bit differently. And is equal to, again, same thing. So just two different ways we can write this out. Now, if I rearrange this a little bit, I can express it also like this, just moving the initial concentration over. And this should start, or maybe is starting to look sort of familiar to you. Y equals mx plus b. And okay, so I have that. I can actually graph this out. And that's the whole point here, is looking at this linearly. Natural log of A given some amount of time. And of course, because as time progresses, the amount of the reaction is going to slow down. So even using this format here, the natural log of A, it produces a linear relationship. So the gives us a negative slope. So we're going to see as the reaction proceeds with time that the natural log of A is going to decrease. All right, that's a pretty good place to take a break for this video.